Most people think they understand their phone battery because they interact with it constantly. You plug the phone in, the percentage goes up. You unplug it, the percentage goes down. When it reaches 0, the phone shuts off. When it reaches 100, it feels finished. The battery is treated like a fuel tank with a visible gauge. Charge it, use it, repeat. That mental picture feels practical and sufficient. It explains why people worry when the number turns red, why they look for outlets in public places, and why battery life has become a basic measure of whether a phone is good or bad. But that picture is incomplete. The number on the screen is not a direct measurement of stored energy. The charging process is not simply filling an empty container, and battery performance is not governed by a single component acting alone. What appears to be a simple object doing a simple job is actually a tightly managed system. It is shaped by chemistry, software, heat, electrical limits, and long-term wear. The battery is not just a component. It is part of an ongoing negotiation between the phone's hardware, its operating system, and the physical limits of materials. The common way people think about phone batteries comes from older technologies. Disposable batteries and early rechargeable ones behaved roughly like fuel tanks. You used them until they were empty. You recharged them until they were full. The relationship between time, usage, and remaining power felt mostly linear. If a battery lasted 10 hours yesterday, it should last 10 hours tomorrow. If it was half full, you could expect about half the runtime. That logic carried over when smartphones arrived. The battery icon reinforced it. A bar that slowly drains. A percentage that ticks downward. The expectation is stability and predictability. People assume the battery itself determines how long the phone lasts, and that the phone simply consumes power until there is none left. This mental model also suggests that charging is straightforward. Plugging in the phone pushes energy into the battery until it reaches capacity. Faster chargers are assumed to be stronger versions of the same process, like pouring faster into the same container, and battery health is often imagined as a vague concept, something that slowly gets worse, but without a clear mechanism behind it. In reality, almost none of this is how the system works. The battery inside a phone is a lithium-ion cell, and it behaves very differently from a simple reservoir. Lithium-ion batteries are sensitive systems with narrow operating ranges. They do not like being fully charged. They do not like being fully empty. They do not like heat. They do not like high current for long periods. And they degrade not just with use, but with time and conditions. Because of this, modern phones do not allow the battery to operate freely. They manage it constantly. The percentage you see is not the battery speaking directly. It is an estimate produced by software. That estimate is based on voltage, temperature, recent usage patterns, and internal models of how the battery is expected to behave at its current age. The battery itself does not know what 50% is. It produces a voltage that changes depending on how much charge is stored and how much load is being applied. That voltage curve is not linear. It flattens in some regions and drops sharply in others. Under heavy use, the voltage can dip temporarily, even if the battery is not close to empty. Under light use, it can appear stable for long periods. The operating system interprets all of this. It smooths the data. It predicts behavior. It hides instability, so the user experience feels calm and consistent. This is why battery percentages sometimes stay the same for long stretches and then drop quickly. It is also why phones can shut down unexpectedly at higher percentages when the battery is old or cold. The system is making decisions based on safety margins, not just remaining charge. Charging works the same way. When you plug in your phone, the charger does not simply push power into the battery. The phone negotiates how much power it will accept. Early in the charge, when the battery is relatively empty, it allows higher current. This fills the battery quickly. As the battery approaches higher charge levels, the system deliberately slows the process. Current is reduced. Voltage is carefully controlled. Heat is monitored continuously. That slow final stretch from around 80% to 100% is not inefficiency. It is protection. For lithium-ion chemistry, high charge levels put stress on the internal structure of the battery. The closer it gets to full, the more damage additional charging can cause. The system trades speed for longevity. Even the concept of full is managed. Phones rarely charge the battery to its true maximum capacity. They stop short. That visible 100% is a safe ceiling chosen to reduce wear. Over time, as the battery ages, that ceiling may be adjusted further to maintain stability. The user sees a familiar number. The system sees a constantly shifting set of limits. Heat is one of the most important hidden factors in the system. Every action the phone performs generates heat. Charging generates heat. Running applications generates heat. Being left in a car generates heat. Lithium-ion batteries degrade much faster at higher temperatures. Because of this, the phone continuously balances performance against thermal conditions. When the phone gets warm, charging slows. Performance may be reduced. Background processes may be delayed. These changes are often subtle, but they are deliberate. The goal is not just to keep the phone comfortable to hold, but to prevent long-term damage to the battery. Battery aging itself is also misunderstood. A battery does not lose capacity because it is used up in a simple sense. Its internal structure changes. Lithium ions move through microscopic pathways inside the battery during charging and discharging. Over time, those pathways degrade. Some lithium becomes trapped. Internal resistance increases. The battery can still hold energy, but it can't deliver it as efficiently. This is why older batteries behave unpredictably. They may show a reasonable percentage, but struggle under sudden load. Opening the camera, making a call, or running navigation can cause a voltage drop large enough that the system decides it is safer to shut down. The battery is not empty. It is unstable. To manage this, the operating system adapts. It learns how the battery behaves over time. It adjusts performance expectations. It may limit peak power draw to prevent crashes. This is not the battery failing silently. It is the system actively reshaping behavior to maintain reliability within shrinking constraints. All of this creates second-order effects that people notice but rarely connect back to the underlying structure. Battery percentages feel less honest over time. Charging patterns seem inconsistent. The phone feels slower when the battery is older. None of this is accidental. It is the visible surface of a system compensating for physical limits. It also explains why usage patterns matter more than people expect. Frequent short charges, overnight charging, heavy use while charging, and exposure to heat all influence how the battery ages. Not because of moral choices or bad habits, but because each condition pushes the battery closer to its stress boundaries. The system absorbs that stress as long as it can. Eventually, its room to compensate shrinks. Another effect is that battery life becomes less about capacity and more about predictability. A newer battery with slightly lower capacity but stable behavior can feel better than an older battery that technically holds more energy but cannot deliver it reliably. The system prioritizes consistency because unexpected shutdowns are more disruptive than shorter runtimes. Seen this way, the phone battery is not a passive resource being consumed. It is an actively managed component within a larger control system. Software, sensors, and hardware cooperate to keep the device functional across thousands of charging cycles, changing environments, and unpredictable usage. The simplicity of the interface hides that complexity because exposing it would make the device harder to live with, not easier. Understanding this shifts how the battery is perceived. The percentage is not a promise. It is a negotiated estimate. Charging speed is not just about wattage. It is about thermal headroom and chemical stress. Battery aging is not sudden failure, but a gradual tightening of operational limits that the system works around until it cannot. The phone battery appears small and mundane, but it operates at the intersection of chemistry, electronics, and software control. Its behavior reflects design trade-offs made to balance speed, safety, lifespan, and user experience. What looks like a simple number ticking down is actually the visible trace of a system constantly adjusting to keep a fragile component working inside a powerful device.